Hello, my name is Rishabh Gupta. I'm a PhD candidate in the Department of Chemical Engineering and Material Science at the University of Minnesota. In this presentation, I'm going to talk about the work my advisor, Dr. Chi Zhang, and I've been doing in developing solution methods for data-driven inverse linear optimization. So before moving into the technical details of our work, let me start by talking a little bit about the concept of inverse optimization and what really motivates us to explore the idea. Decision making is something that is fundamental to everyday life. As humans, we are very good at quickly analyzing various trade-offs involved in a decision to achieve the best outcome for ourselves. While we get this ability through years of experience, in most cases, the process we use to arrive at our decisions remain unknown. Now, how a person makes such decisions can obviously be useful for various purposes. I'll show some examples in my next slide. But the question of interest here is, can we use the data from past decisions that we have observed to uncover the underlying decision-making process? Now, inverse optimization provides a way to answer this question. And this approach is motivated from the principle of optimality, which conjectures that all autonomous agents generally make decisions in some optimal fashion. In other words, the idea is that the autonomous agents, they actually solve an optimization problem to arrive at their decisions. So therefore, in inverse optimization, we fit an optimization problem on the data such that the optimal solutions of the estimated optimization problem closely replicates the decisions being observed in reality. Now, here one question you may ask is that the problem I just highlighted of uncovering the underlying decision-making mechanisms is nothing but a machine learning problem. Then why exactly are we interested in this approach when there are several pre-existing machine learning tools? The reason is simple. Although the ML methods are very effective, they tend to be data intensive and end up producing models that are difficult to interpret. In contrast, if we can represent a decision-making process as an optimization problem, it helps deal with most of these issues. Let's consider the two examples shown on the slide. The first is the problem of learning preferences of your customers. Economists typically model customers as utility maximizing agents, and therefore one can write an optimization problem like this to describe their behavior. Here, constraints typically represent restrictions on budget or product availabilities, which are easy to model. The only thing we need to estimate here is the utility of the customer. The next one is the case of imitation learning or learning from experts. Specifically here, we consider the case of an expert operator generating production plans for a manufacturing plant. Again, the constraints represent the physical limitations on the system and can be easily modeled as long as the physics of the process is known. But the thing we want to know are the production costs, which are often difficult to estimate. This is in fact one of the major reasons why in practice production planning is still being performed by human planners. If we look at these two problems, writing them out as optimization problems provides them with a nice and interpretable structure. The hope here is that because the constraints are allowing easy incorporation of existing domain knowledge into the models, the amount of data required to come up with a good model will be significantly less compared to what a black box model may require. Okay, so now let me switch focus and introduce the specific problem that we consider in this work. While the underlying optimization problem can take any general form, here we restrict ourselves to linear problems. We assume that the underlying data generating process has this form. The decision maker is minimizing the cost C transpose X subject to a set of constraints AX less or equal B. In this model, X are the decision variables and A and B are the input variables. Now these input variables are things that you can control and can change to extract more information from the decision maker. For instance, if we consider the case of modeling customer preferences, one can change the prices to see how the behavior of the customer evolves with the changing prices. Now in this work, we consider that the structure of the constraint matrices is known, and the only thing that is required to be estimated is the cost vector. Now to develop an estimate for the missing cost vectors, what we can do is we can collect multiple observations from the decision maker corresponding to different values of the input parameters A and B. We refer to every new perturbation of these experiments as an experiment in this work. Now this slide shows our formulation for the inverse linear optimization problem. The first step in our approach is to estimate the feasible region of the inverse problem that consists of all the non-zero cost vectors that will be feasible to the inverse problem. And we do this by solving a minimum distance projection problem here. Now here I is the set of experiments and J sub I is the set of observations selected for an experiment I. What this problem actually does is project the observed data xij for an experiment I and sample j on the solution space of an LP to be estimated. Now, assuming a non-zero C, the solution space of a linear problem consists of the boundaries of the feasible region. But here we actually put a restriction that the projection should only happen on the vertices of the polyhedron. Now, by solving this problem, we get a set of feasible cost vectors, which we transfer to the second step here, in which we take the admissible set of all the cost vectors and use a reference cost vector C bar, which will be based on any prior knowledge or assumptions that the user has about the cost parameters to choose a C hat that is closest to the C bar. Now, the C bar will be the final estimate for the missing cost parameters that we will generate from this process. Okay, so what does this process look like geometrically? Let's consider a case where we have two experiments with 4 noisy observations in each experiment. The polytopes here show the feasible region and the circles are the noisy observations. And this is the true cost vector that is being estimated. When we solve the minimum distance projection problem for this example, these data points actually get projected to the nearest vertices like this. And after getting the denoised, the respective denoised estimates of the data, which are shown in these solid circles, we can tell from our LP101 class that the real C must lie in these normal cones at the vertices. Since we have two experiments, the admissible set shall be the intersection of these two cones, as shown here. And as one can see, the intersection of these two cones is also a cone, and therefore we can say that the admissible set will be a polyhedral cone. Now, once we have this admissible set, we move on to the second step, in which we use a reference C bar to choose a C hat from this admissible set. Now, given the way C bar is shown here, C hat would be C bar itself, but this was just for this example. The C bar could even be outside depending on the quality of your prior. Now, this slide shows the algorithm we use to solve the inverse problem. This essentially works the same way as I described the formulation. There are two phases in this. First, you denoise the data, following which we find an estimate for C. The key detail to note here is that the phase one problem is a mixed integer program, which we get by reformulating the pi-level minimum distance projection problem by using the KKT optimality conditions of the inner level LP. Now, this problem size, it actually grows with the number of experiments. And one can expect that higher dimensional problems will require more data. And hence, as the dimensionality of the forward problems increase, this problem becomes intractable. Therefore, in this work, we consider a decomposition algorithm for this problem. So I'm going to explain this algorithm geometrically. So we are looking at an example with 3 experiments. And to keep things simple, we do not show the noisy data on the figure. The true cost vector is shown here on the right. So in our decomposition method, we denoise the data from these 3 experiments one by one sequentially instead of solving them all at once. So essentially at every step, we are solving a simple projection problem of finding the nearest vertex without caring about the fact that there must be a common C among the 3. This would work for most cases where the quality of data is good. For example, in the first 2 cases, one can see that with this true C, the projected X are really the true solution. However, once in a while, you may have a case where the data is really noisy, and when you solve the projection problem, the projections ends up happening incorrectly. For instance, in this third case, the true solution is this vertex on the top, but the projection happens on this vertex. But as it turns out, there is actually a very easy way to detect these errors. As shown here, while the true cost vector C lies in the two cones, intersection of the two cones resulting from the correct projections, the intersection of all three cones, including the one associated with the incorrect projection is a singleton containing only the trivial solution 0. Now this is a problem because when we solve all three of these together, the projections, these projections will progress in a way that the admissible set is not just a trivial solution. So using this insight, at every step of this sequential algorithm, we use a feasibility problem to check whether the admissible set is non-zero or not. Whenever we encounter a case where the admissible set contains nothing but the trivial solution, we solve the full problem with all the experiments considered up to that point to correct the error. So even though this algorithm may occasionally require to solve large instances of the projection problem, here we can actually use the previous projections to warm start the solver, which actually significantly improves the computational efficiency of the process. Now, an important thing to note here is that this algorithm provides a natural extension of our approach to enable sequential learning or online learning, where the data from different experiments become available at different time points. So this algorithm was for improving the computational efficiency of the learning process. Another thing we consider in this work is adaptive sampling to improve the sampling efficiency. Now, if we again consider this example with 3 experiments, notice that the admissible set, the script C, obtained with the first 2 experiments is the same as the one obtained with all 3 experiments. Therefore, this third experiment is not adding any value to the process. It's not helping me to learn anything new about the missing parameters. So to avoid such wastage of sampling effort, we make use of we make use of our geometrical insights into the structure of the admissible set to design an adaptive sampling strategy. So let's suppose that the script C is the admissible set at some point during an online inverse optimization process. After this, whenever we add a new experiment, let's say this new experiment is the admissible set for just that experiment is script C bar. So for this script C bar, there are 2 possible scenarios. Either the cone from this new experiment looks like this, which actually does not reduce the size of the cone script C, or it can look like this, in which case, after we take the intersection of these 2 cones, script C will become smaller. And we always want this scenario to occur. So in other words, what we want here is that the intersection of these 2 cones, script C and script C bar, should be a strict subset of script C. So we actually formulate this problem of finding input parameters that can result in such a set script C bar as a mixed integer nonlinear program, which for which, in the interest of time, I'm not displaying the formulation here, but instead directly proceed to show some computational results. So first is a comparison of computational performances of the full space model and the decomposition method. So we do this by generating random instances of the customer preference learning problem. So we vary the difficulty level of the problem by considering forward problems of various sizes and training data with varying levels of noise. The plots here show the computational time requirements for each of the 10 random instances we considered for the study. Now the circles here circles are for the decomposition algorithm and the squares are for the full space model. You can also notice some hollow markers, which indicate the cases for which the solution method could not even find a feasible solution in the allotted time. So as one can see, for lower dimensional cases, the 2 have a comparable performance. However, as we move to larger problems, decomposition method starts outperforming the full space model. The difference in their performance is even higher when you solve cases with bad data. For this most difficult case that we consider in our study with large problem sizes and high noise in the data, full space algorithm could solve only one instance, whereas the decomposition algorithm solved 9 out of the 10 random instances that we considered. This slide shows the effect of adaptive sampling. The plot shows the change in the prediction error of the estimate as more experiments are added to the problem. Now, this prediction error was calculated as the fraction of incorrect predictions of decision variable values across 100 unseen instances of the forward problem. Now here, solid lines show the result for random sampling and others are for adaptive sampling. As one can see, adaptive sampling across the board provides more than 50% reduction in the sampling requirement to provide same prediction accuracy as random sampling after 100 experiments. So we also tested our method on an instance of the production planning problem that I briefly talked about in the beginning of my talk. It is based on a large petrochemical site with a process network consisting of 38 chemicals and 28 processes. The plot on the left shows how the prediction error evolves with random sampling for forward problems of different sizes. The T here indicates the number of time periods considered in the case study. Again, we see that with the constraints specified, I can generate reasonably good predictions in just under 100 experiments. Also, the adaptive sampling plot shown here on the right also shows the variance of the prediction error around the mean. Clearly here, if we compare the two sampling methods, adaptive sampling not only reduces the sampling requirement, it also produces an estimate with much higher confidence, which is apparent from the noticeably lower variance around the mean for the red curve. Okay, finally, we have the conclusions. So in this work, we introduced a new framework for data-driven inverse linear optimization with noisy observations. We provided a decomposition algorithm and an adaptive sampling strategy to make the entire process more efficient by reducing both the computation and sampling efforts. In case you're interested in learning more about our work, a preprint of our paper on this work is available on arXiv. And we welcome any feedback and questions. Please feel free to reach out us at our email addresses shown here. And for now, I'll just end this talk with the acknowledgements. And I look forward to interacting with you during the live session on November 17th. Thank you.